Welcome back, Cubs. In this video, we're going to be taking a look at the changes of state. Uh, so this slide here kind of covers pretty much quite a bit of information. I'd be very familiar with this slide in preparation for the exam. So solid, liquid, and gas gives a description, a little bit of the kinetic molecular theory. So that's how the molecules are moving. Then also gives us the changes of state. The one that is missing, we have sublimation going from a solid to a gas. The one that's missing would be deposition, and that's going from a gas to a solid. So let's get into the details of the phase changes. So three main states, solid, liquid, and gas. We know that. Plasma is going to be a gas with high energy particles or free-flowing ions. So phase, by definition, it's going to be the portion of a substance that is uniform in composition and properties. So if we were to take a look at the temperature of a particular portion of the substance, we would be identifying the phase for that portion. Okay, so one of the changes is condensation. Some of us have experienced this. A glass of iced tea on a hot summer day, and we see water droplets forming on the outside of the glass. That would be condensation. So where a gas changes to a liquid. So the water vapor found in the air is going to condense on the outside of the glass due to the temperature difference. And then equilibrium. So equilibrium occurs when opposite changes within a closed system are the same. So it might appear that we have two separate phases there, but we'll still have some change happening, but it's in equilibrium. So that means particles, reactants will form products, and products will form reactants here, but it's at the same space or at the same rate. Usually we're used to seeing changes happen kind of with this first example here, where more of the reactant is going to form product, or more product and less reactant. But we can also have equilibrium here. So it's where opposite changes are occurring at the same rate. This comes into play with the equilibrium vapor pressure. This is the amount of pressure exerted by a gas and a liquid at a particular temperature when equilibrium. So that means that the gas molecules and liquid molecules, if they're at EVP, they're kind of going back and forth between those two phases there. And molecules within a substance are going to be attracted to each other. So this could be through intermolecular forces, like dipole-dipole forces or hydrogen bonds. And if we have a greater attraction, then fewer particles will leave the liquid. So this is why water has such a particular high boiling point based on its molar mass. If we did a comparison of the molar mass of water and the molar mass of, let's say, methane. So a molar mass of water is going to be 18.02. Molar mass of methane is going to be 16.01 or 0.05 grams per mole. So they have very similar molar masses, yet one has an incredibly lower boiling point. That would be methane. Methane has a lower boiling point than water because of the lack of intermolecular forces. Remember that water is a highly polar molecule. Because it's highly polar based on the oxygen-hydrogen bond there, it's going to experience hydrogen bonding. Remember, that's the attractive force between the negative dipole region of one water molecule and the positive dipole region of another water molecule. So because of that attractive dipole-dipole force, there's greater attraction, which means fewer particles will leave the liquid. It requires more energy for a particular particle of water to leave its liquid state. Volatile liquids, those readily evaporate because they don't have those strong attractive particles or strong attraction between the particles. So methane would be an example of that. So the next change we'll discuss is boiling. Conversion from a liquid to a gas within the liquid and at the surface of the liquid. So boiling point, this is the temperature. Remember, we're concerned with temperature and kinetic energy here within the kinetic molecular theory. So it's the temperature at which the equilibrium vapor pressure is equal to the atmospheric pressure. So that means if there's lower atmospheric pressure, then a lower boiling point. So what kind of real-life applications would that have? Well, lower atmospheric pressure. So if you're higher up in the mountains, you would have a lower atmospheric pressure. That means you would have a lower boiling point. So the water would boil at a lower temperature. So think about this question. Would it take a longer time to boil pasta in Denver than here in Michigan? Think about it. If you email me the answer, I'll give you a bonus point. So energy must be continuously added to continue the boiling. And then let's introduce STP here, that's standard temperature and pressure. So this is going to be normal atmospheric pressure at 1 atmosphere, or ATM, and 0 degrees Celsius. So here we can see increased pressures increasing the boiling point. So on this graph here, as the pressure increases, the temperature also increases. That's why we see a positive slope on this particular graph here. Then we also have the molar enthalpy of vaporization. So this is the amount of energy required to vaporize 1 mole of a substance, indicated by delta H sub V. So it's the amount of energy that's needed to vaporize 1 mole of a liquid into a gas. And we can use this value as a measurement of how attracted the particles are to each other within a substance. So just like we would use the melting point to measure the attractive forces of the solids, we can use the molar enthalpy of vaporization to measure the attractive forces within a liquid. And then on this phase diagram graph here, just a reminder, if we're going from a solid to a liquid, melting, liquid to a solid, freezing, liquid to a gas, vaporization, gas to a liquid, condensation. We have this triple point that we'll discuss in a moment, and then sublimation and deposition. Notice the red arrows here are also referencing an increase in kinetic energy or an increase in temperature. That means the particles are moving around more. The blue arrows indicate a decrease in kinetic energy or a decrease in temperature. So brief discussion on freezing and melting. Freezing involves the loss of energy. So we're removing heat or temperature or energy from the system. As the energy decreases, the kinetic energy also decreases. The particles stop moving as much. And that particular point where the solid and liquid are going to be in equilibrium when we remove that energy is going to be the freezing point. So it's the temperature in which the solid and the liquid are in equilibrium. Referencing this back to energy, the overall kinetic energy is decreasing when we go to a liquid to a solid. Liquid into a solid, energy's got to be given off somewhere. And then melting, if we have a solid and we apply energy, perhaps in the form of heat, and if it's enough, we can get a liquid. And we can measure how much energy is required by the molar enthalpy of fusion. Delta H sub F in this case. And then one of the cooler phase changes is going to be sublimation and deposition. So under very low temperature and pressure, liquids cannot exist, so the substances will go directly between a solid and a vapor. That's going to be known as sublimation. Then deposition, that's when we remove energy from the system and it goes from a gas directly to a solid. Now, it doesn't necessarily have to be at a very low pressure. We see with dry ice, solid carbon dioxide, that will directly sublime from a solid to a gas at room temperature and atmospheric pressure. So phase diagrams. So within the phase diagram, this tells us the changes that we can have for a particular substance, going from a solid to a liquid to a gas. And then we have this triple point here, and then the critical temperature and critical pressure. On this graph, if we were to follow along at 1 atm, so at 1 atm below zero, we would have a solid. Between 0 and 100 at 1 atm, we would have a liquid. And then above 100 degrees Celsius, we would have a gas. If you email me what substance I'm talking about here based on those temperatures, if you email me what substance this is, I will give you a bonus point. Okay, so get comfortable with being able to identify these phase changes here on this particular chart. You might see it again, or the same type of information might appear on your exam. So let me know if you have any questions, guys. You can email, remind, or discussion board. Have a great day, Cubs.